So in this, our third lecture on time series models, I'm going to continue to think about this state space Bayesian modeling framework, also called the hidden Markov model. We're going to move on to a slightly more interesting, less trivial example. Previously, we had talked just about a random walk state space model. We're now going to move on to a model that actually represents population growth. But before I do that, just want to remind you the basic framework of the state space model. We have a process model that predicts how the state of the system X evolves through time. So it's dynamic. Y X of t is some function of X of t in the past and possibly with potential lags plus some observation error. But these X's that are evolving through time are themselves latent, they're not observed directly. And then we have this data model that links our observations of our observed data Y to our X's, our latent time series with some observation error. And that in many cases, Y of t and X of t are the same direct variable being measured. And so we just have some observation error. But this framework can accommodate more complex data models such as calibrations between some instrument measuring Y and some true X, or some proxy data, or more complex relationships between what we're actually interested in modeling and what we're able to observe. So as I said, in this example, we're going to dive into a slightly more interesting state space model, and we're going to essentially start from what is often the most basic population model that folks learn about in say an intro ecology class, which would be the exponential growth model. So this is written down as a differential equation where d n dt, the change in the population over time, depends on the current population size n and a growth rate r. And this has an analytical solution that gives us an exponential relationship between time and population size, growing at this exponential rate. But it's often the case that population models, instead of being written down as differential equations, are often approximated as discrete time recursive models. So I can approximate this dn dt Rn by instead writing down some model of n at t being some function of n at t minus 1 and some growth rate, and allows me to simulate that. In this case, if I let x be the log of n, so we transform things from a linear domain to a log domain, I can transform this exponential growth model in discrete time to x of t is x of t minus 1 plus some r plus some error. So instead of, when we take this e to the r, we just get, we take the log of e to the r, we just get r back. And this, putting the error on here in the log domain essentially corresponds to putting a log normal error on n0, on the n's themselves, which is sensible here because populations are going to be zero bound. It doesn't make sense for them to be negative. And they often do show this pattern of the log normal of being skewed, and also of the variance increasing as the size of the population increases. I'm going to write down a simple observation error model, assuming that y is related to x directly, but with some observation error w. And again, this little r is the intrinsic population growth rate. Y is now also has to be in a logged scale, so y is our logged observations. And also pointing out that you could conceivably, in this framework, interpret the process error as actually a random effect on the parameter R. So you could actually interpret this as what we're seeing is that X is evolving from time point to time point with some mean growth rate R, but that mean growth rate, population growth rate, is not constant through time. Sometimes the population grows faster, sometimes the population grows slower, for reasons that are not captured yet in the model. So again, we can now think about modeling the variability in the parameters in this particular structure. So the graphical version of this looks very similar to what it did for the random walk model, with the addition that we now have a parameter R in addition to the parameter sigma as part of our process model. Also noting that I've highlighted the variables affecting X, XT in red to again highlight the three things that are used, the three likelihoods that come into play when estimating X of T. Those latent states are constrained by the previous time point, by the next time point, and by the observations. So let's look at how this plays out with some simple simulated examples. So here are just what some simulated time series from this model might actually look like. So this isn't fitting models of data, this is just simulating data to give you an idea of what happens as we vary the relative balance between process error and observation error. So in this example, I'm setting little r at 0.1, so a 10% population growth rate, but I varied the process error from 0.01 to 1.0. So in the first run, there's very little process error. It's dominated by the process model, which is an order of magnitude larger than the process error. And we see a very, almost a very deterministic growth in the population with very little apparent variability. In the second run, we set the process model and the process error to be similar. So we see that the process model is continuing to drive us upward year after year. But we do see a good bit of variability, that even though, for example, here around time point, 10, even though the mean population growth rate is positive, we see a couple years where the population declines. And that's just because we've added additional process error. There's things in the process that beyond the process model. And in this third run, the process error is larger than the population growth rate. So in some sense, the process error is larger than the process model. The simulation is dominated by that process error. You can see, there's still a slight hint of an upward trend in the population, but we're seeing a lot of variability. And that's a place where, clearly if process error is dominating the dynamics of the model, there's something that is missing from that model, because most of what we're seeing is process error, which again implies that there's something not captured. And that process error could be something reducible, things that we are missing from our model that we could add, or it could be something irreducible. It could be that process error represents true inherent stochasticity in a system that is actually truly hard to predict. So now let's look at what happens when we start fitting state space models to data. Here's a case where I think I left little r at 0.1. I've now set a process error that's non-trivial, so to give us a good bit of variability in here, and then set a tau around that as well. So I'm adding some observation error, and for starters, I'm assuming the observation error is smaller than the process error. That most of these wiggles are real wiggles, not just noise in the data. So if we fit this as a as a non-dynamic process, if we just fit this as a data set, we would do something simple as just fitting a straight line through this. Or if we fit this in a way that didn't account for process error, even if we fit a traditional exponential model that is a truly dynamic model, but one that does not have an inclusion of process error, if we fit, essentially, if we fit the exponential growth model as a prediction of a line rather than a prediction of a process, then our best fit would end up being a straight line, which is clearly missing true variability in the process. By contrast, if we fit this same data set in the state space framework, what we end up getting is something like this. So here, the black line is that simulated true latent state of the system that is evolving through time. The red dots are a simulated observations around that true state. And so that's the difference between the black line and the red dots, is that inclusion of observation error in the model. So, here we can see it about, I don't know, what is this, about 27 or 28, an example of a data point that even though the true latent state of the system, the observation is a good bit higher than the true state of the system because there's observation errors. And other points around 20, it's lower, and then other times it's close by or very close to that black line. Again, this was a simple simulated example where I set that observation error to be relatively small, but showing that we're adding that observation error. To the state space model, when we fit this model to data, it only sees the red dots. You only see the observations. But what you get out of this, we get out of this a posterior estimate of tau. We get out of it a posterior estimate of sigma, our process error and observation error. We get out of it a posterior estimate of R. So here is our posterior distribution of R, and here is its true value, the one that we use to simulate this data at 0.1, and we can see that our posterior distribution for that in this case is very close to the true value. It definitely overlaps the true value, so that's encouraging. We're actually able to recover the true parameters of the system in this case. But then we also get a posterior estimate for every x. So this green line that we're calling the fit is the mean and confidence interval for every single x. And we see that at every point in time that, well, we definitely don't have just a straight line, that our best estimate of the state of the system is wiggling up and down with the data because, well, for one thing, because the x at any point in time is informed by the x above it and the x below it and the y, but also because that framework is acknowledging the reality that our process model is representing a process of how the population grows through time, acknowledging that there is uncertainty in that process. It acknowledges that our process model is not perfect and that there is process error. And that acknowledgement that there is process error means that our best fit of the process does acknowledge that even though the R by itself would predict a linear upward trend, that the population can be going up and down through time, and that's real. It's not observation error. The other nice thing about this framework that we've talked about conceptually, but we haven't looked at, is what happens when there's missing data. So here, I just removed a segment of observations and asked the model to infer what was happening over that time point, over this gap in data. And the state space model handles this very seamlessly. It has little choice for the mean to do anything other than to expect that to move along that upward trend driven by R and the upward trend driven by the fact that the only two observations it has do show an upward trend. So it's both interpolating between these 2 points and leveraging the fact that our estimate of R implied that they were growing. But then we have this, what I often call a classic kind of balloon shape confidence interval around missing data in a state space framework. So if you think what's happening here, at this point in time, kind of 2 before the gap, this X is informed by the X before it and the X after it. When we get to the X right on the edge, it's informed by the X before it, but it doesn't have the X after it. So the X uncertainty starts to increase. There's less precision. We get into the gap, it's informed by what came before it, but there's nothing after it. And so the uncertainty starts increasing as we move into the gap. By contrast, as we get closer to the other end of the gap, that uncertainty starts narrowing back down again, because remember, the state space model does use observations from the future to inform the current state of the system as well. So we kind of have this almost kind of balloon animal shape or kind of football shape of a confidence interval where it starts narrow and it spreads the larger the size of the gap, but it comes back down at the other end. And then we can extend this framework to prediction very easily. I guess before we get to prediction, I want to note that in this case, even though we can't capture the wiggles in the true state of the system over the missing data, we actually have a confidence interval that does a very good job of containing all the true observations. Oh, so this last point is that to move our state space model from fitting to prediction is, again, very straightforward. You can seamlessly do it because you just move to a case where you're constrained by points on both sides. You're constrained by a point on one side, then you're just constrained by what happened before without being constrained by observations. And then we have this kind of increase in uncertainty as we move into the predictive mode. And we can also see in this case that the trend from the little R0, the intrinsic growth rate kind of is driving this prediction forward. In practice, you can easily do that 2 ways. You could either fit this model's data and then take all of your posterior estimates, your posterior estimate of this X and this R and the process error, and simulate it forward just as a simple Markov process into the future, using our standard Monte Carlo simulation techniques. So it's just a simple Monte Carlo confidence interval. Alternatively, you can do this in JAGS by just feeding in this whole time series of data and then just setting all of these Ys to NAs the same way as you set these Ys to NAs. So in JAGS, you accommodate this missing data by just saying that this Y was NA, that Y was NA, that Y was NA, and then it goes and treats that as missing data. And then you can do predictions by just treating the future as missing data as well. So we've seen a couple examples of the state space model now, a simple random walk and a simple exponential growth model. I wanted to point out some generalities. I mentioned some of these earlier, but I just wanted to reinforce them. So first, neither X, the process error, or Y, the observation error, need to be normal. You can have any likelihood you want on the data model and any shape to the process error that you want. X and Y don't need to be the same type of data. One thing that's very common might be for X to be continuous and Y to be discrete. So if you have, counts of individuals in a population, you would have discrete counts of Ys, and but you have a continuous density underlying that. And you might then end up with say, normal process error and a Poisson data model. X and Y don't have to be on the same time scale. That this framework easily accommodates missing data, irregularly spaced data, gaps in data, process models that evolve on faster timescales than our observations. As we've noted, noted again, easily handles missing data and irregularly spaced data. It also, we'll see later, easily handles multiple sources of data. So very much like what we talked about at the end of our section on hierarchical models, where we had a data fusion example where we had multiple data models. If we have some latent time series X, we could have a data model connecting it to one set of Ys. We might have a data model connecting it to some set of Zs, a data model to connect it to some other set of data. And they don't necessarily need to be the same type in the sense that they don't have to have the same observation errors, and they don't have to be synchronous. So I can have a Y at one time point and a Z at a different time point, or I could have both the same point, I could have neither. And we'll also talk later about how we can use the state space framework to handle what are called time integrated observations, which would be a case where what you observe at Y isn't the instantaneous state of the system at Y, but perhaps the mean over the period since you last observed Y, or the sum or the integral over the time since your last observations, which is something that can happen pretty commonly with a number of different observation techniques. That's it, and we'll continue on from there.